AP Chem Series. This is Mrs. Vanderwall bringing you another edition of Blank Wall. Today we're going to finish off 5.6. We did not get done with Dalton's law of partial pressures today, so we need to finish off this work. Actually, this is kind of important for what we're going to do in lab tomorrow. We're going to start off with problem number 22, and as always, do the work yourself before you check out your answers. Work through these problems. If you have questions, write them down and we'll get to you as soon as we can. Or even if you will, text me. I know that some folks have caught some of my boo-boos in the past. We try to fix them right away. All right, problem 22. We have two containers. One has helium, the other one has oxygen. The first container has 46 liters of helium at 25 degrees Celsius in 1 atmosphere. And the other one has 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere. We're going to take those two containers and squeeze them into a smaller container that's only 5 liters. So no, volume went way down. I will expect to have a fairly large new pressure. So we are then to calculate the partial pressure of each gas and the total pressure in the tank. Well, automatically I'm seeing a volume, temperature, and pressure of helium, volume, temperature, and pressure of oxygen. What do you think you're going to solve for? What's your missing variable? Yes, it's moles. So why don't you set up two Pivnert equations and solve for moles of helium and solve for moles of oxygen? Then come right back. So how'd you do? Hopefully you got moles of helium was 1.88 and moles of oxygen is 0.490. I got moles of helium. I have moles of oxygen. They're together in this new tank. So I bet we can come up with a mole fraction, could we not? So why don't you go ahead and figure out the mole fraction? And we also need to calculate the total pressure. I bet we can do that by finding the total moles and find the total pressure. So go ahead and set up another Pivnert. Use your sum of your moles to find total pressure and use your chi's to come up with the partial pressures. So once again, I used the Pivnert equation and I found that the total pressure times 5 liters is the total. It's 2.37 moles. Where did I get that? The 1.88 plus the 0.490 from the helium and the oxygen. And I solved and I got the new pressure is 11.6 atms. Okay. From there, we need to solve for the partial pressures of each. Again, we told you how to do the mole fraction. Go ahead and set that up for each of them. So pause this, figure it out, and check back in. All right, so now that I knew what the total pressure was, I can go ahead and find the partial pressure of helium and oxygen. I found the total pressure is 11.6. Chi was the moles of helium over the total moles. We already found that, 2.37. I used that in the previous Pivnert. And voila, I got 9.2 atms. Find out for oxygen, I did the same thing, and I got 2.4 atms. Hey, what do you notice when you add together 9.2 and 2.4? Add those two partial pressures together, and indeed you get 11.6. Should be no surprise there. Look at number 23 and try to figure it out on your own. It's easier than you might think, okay? So look at it, try to solve it, and see how you do. Here I use the same equation again. Partial pressure of oxygen equals the total pressure times chi. Plugged in my numbers. Notice my torrs are going to cancel out. The units cancel out, so chi is unitless. I get 0.210. Yes, it really was that easy. Let's go ahead and do number 24. Look, no calculator. So we have a reaction going, and we're asked to figure out what is the pressure. Folks, I just want to show you real fast. The ATMs is like the whole quantity put together. It's not 4 ATMs. You're not dividing by 4 ATMs. ATM is the unit. So I see an equation. Ding, 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 ding. What should come to mind immediately? BCA table. Yes. So go ahead and set up a BCA table and figure out what your limiting reactant is. Which reactant is in excess and how many moles of product do you make. So go ahead and set that up. See how many moles of stuff you still have in your container. Okay, so here's my BCA table. What does it mean? My limiting reactant is actually sulfur dioxide. I have 0 moles of that left. But look, I have 0.10 moles of oxygen still in the container unreacted. I made 0.20 moles of sulfur trioxide. So what is in my container? None of this. Hang on, let me get a pen going. All right, so I have none of this. I have 0.10 moles of oxygen floating around, and I have 0.20 moles of sulfur trioxide floating around. So how many moles of gas do I have there together? Looks like 0.3 moles. So I'm really looking at B or E. The other ones don't have the 0.3 moles. This is like PIV NERT sulfur P. Here's my moles, RT divided by L. What's really the only thing that changes is my T value. This is 298, this is 25. Hopefully you say, well, that's dumb. They didn't convert to Kelvin. So B is your final answer. I really do like this, excuse me, the next question here. I've seen this before on AP exams, so we thought we better bring this back to you. So it says, using the information provided in the diagram below, provide the partial pressure of helium and argon after mixing and the total pressure in the flasks. All right, so this is my understanding, and the math works out, that these are not balloons. Their volumes do not change. Okay? These are rigid containers that have a valve in there. So the volumes themselves, the circle here will not change. The size of the circle will not change. Look at your after. The volumes didn't change. So what does change? Well, what happens if you open up the valve here? Some of your helium molecules can migrate over into this container. Some of your argon molecules can migrate over into this container. So really, the volume changes for each gas, therefore pressure will change for each gas. Your new volume in each case is going to be 4 liters. Well, where did that come from? 3 liters here, 1 liter here. So you're going to have V2 in both cases is going to be 4 liters. So how are we going to set this up? Just watch. Sorry. So 120 times 3 is 360 divided by 4. Looks like 94, isn't it? Okay. So look what happened. Volume went from 3 liters to 4 liters. So volume went up. Pressure is going to go down. Yes, it did. But I'm not done yet. All right, so in the container, what happened? We opened it up, our volume went from 1 to 4, so volume went way up, our pressure is going to go way down. So our new partial pressure of argon is 20. I'm not done yet. I found the partial pressure of each, argon and helium. What do you think is left to do? What's the total pressure in the flasks? 20 plus 90 is 110. Okay, so that's that particular problem. All right, let's go on to the next page. Okay, the reason why I'm kind of in a hurry is I had to get to this section. You need this information for tomorrow's lab, and that's collecting gases over water. So it says when the desired product of a chemical reaction is a gas, the gas is often collected by the displacement of water as shown below. So if you have any water in the container and your gas is mixed with the water at the bottom, or in your case in the lab tomorrow, you're putting in 5 mils of 3 molar hydrochloric acid. What do you think that hydrochloric acid is made up of? Oh, I diluted it with water. There's water present. So gas is being collected with some water present. Well, what will that water do? That water will vaporize. You're going to have some water vapor in there. And just think of it, on a nice hot day, isn't it usually humid too? Why is that? Because water will evaporate more quickly when it's hot outside. If it's a cold day, is it a humid day? Have you ever had a cold and humid day? I've never heard that on a weather report. Oh, it's going to be cold and humid today. No way. Why isn't it going to be humid on a cold day? Because water doesn't evaporate very well on a cold day. So look what I wrote here. As temperature goes up, the vapor pressure of water goes up. Why? Because there are more water molecules in the gas phase because they're going to evaporate more. So look at the table down here. Look what happens. Temperature is going up. What's happening to the vapor pressure of the water? Yeah, it's going up too. So what is this telling me? As temperature goes up, more and more and more molecules are going to be in the gaseous phase, making the pressure greater. Didn't we already know that pressure and moles are directly related? As more moles are now in the gas phase, we're going to have more collisions, we're going to have more pressure until all the way you get to 100 degrees. Oh, look what happened here. The pressure is 760. That number should definitely ring a bell. So when water is boiling, you have every single water molecule now eventually is going to be in the gas phase. So you have 760. You have 1 atm of pressure. So how is that going to be helpful? Well, let's take a look at problem number 26. You're going to heat some potassium chlorate and you're going to make some oxygen gas. But look at that, not just oxygen gas, but you have a tube filled with water, and when you collect the oxygen gas, you're going to force that water down. So you're going to have the oxygen collected, but you're going to have some water vapor as well sneaking into that gas area, if you will. It's going to evaporate. It does depend on the temperature. So if I'm looking at here, oh, if you collect over water, you have to think of Dalton's partial pressure because P total will equal the pressure of the water vapor plus whatever gas you're collecting. So let's check out what's happening here. We have a sample of this potassium chlorate. It's going to decompose. You're making water. Excuse me, you're making oxygen. What's happening here? You are going to collect it and you have a total pressure of 754. Total pressure. Well, what's included in that total pressure? Pressure of water, pressure of oxygen. So somehow we have to calculate oxygen alone. How are we going to do that? All right, let's figure it out. I'm going to write above the problem. Pressure total. And that water is coming from here. That water is going to evaporate and create some water molecules. How much? It depends on the temperature of the water. So look, the place they go in the pressure, the total pressure is 754, and they told you what it is at 22. It's 21 torr. So from there, can you figure out what the pressure of oxygen is going to be? Hopefully it's not too tough. You're going to get 733. Well, now that we have that, it's fairly straightforward. We have pressure of oxygen, we have volume of oxygen, we have temperature of the container. Hibner, what can you solve for? Moles. Do it. Go ahead and pause this. You figure it out yourself. Okay, fairly straightforward. You should get 0.0259 moles. Am I done yet? No. What are they asking for? They're not asking for moles of oxygen. They're not even asking for grams of oxygen. Oh, periodic table. No, what are they asking for? They're finding mass of potassium chlorate. They want the mass of something besides oxygen. That's a BCA table right there. Set up a BCA table using your moles and then go ahead and solve for mass of potassium chlorate. Go ahead and finish off this problem and check your answers. Okay, so here is my balanced equation. I know I started off with potassium chlorate. I know I made some oxygen gas. So what else was left was potassium chlorate. I had to balance it. So it's a 2-2-3 ratio. Well, I know how many moles of oxygen I have. So tell me how many moles of potassium chlorate I start with. Assuming all of it went. The answer is yes. So take this, divided by 3, times 2, and I get 0.0173 moles of potassium chlorate. Well, guess what? You can have sulfur grams. That's right. That's what this number is from the KCl3. I got 2.12 grams of go ahead and I think we have like one more problem to do. Hallelujah. All right, so we're talking about photosynthesis, gases emitted by plants, over water. Ding, 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 ding. Dalton's law of partial pressure. There's a temperature and a total pressure of 755. So they collected about 1.2 liters of oxygen gas, but mass of oxygen is at periodic table. Yeah. Know that. So again, total pressure collected over water. Dalton's law of partial pressure. So why don't you set that up? All right, so here's my equation. So here's my total pressure, 755.2 millimeters of mercury. Here's my pressure of water. Now, where in heaven's name did that come from? Well, do you remember you had a chart on the page before? Let's look at it. Beep. All right, here it is. Scroll it down a little bit. There we go. Here's the chart. All right, but wait a minute. What are these temperatures in? Those are degrees Celsius. Ruh-roh. What did they give us in the problem? They gave us, where is it, 293 Kelvin. Well, what is 293 Kelvin in Celsius? Subtract 273 and you get 20. So what does it say at 20 degrees here? Here it is at 17.55. So that is the partial pressure of water. It's right there. There's my pressure of oxygen. So 755.2 equals 17.55 plus pressure of oxygen. Pressure of oxygen is 737.65 millimeters of mercury. I bet at this point you don't need me. You're going to plug this into Pivner. Don't forget you have to make your millimeters of mercury into atmospheres. Solve for N. What's N? Oh, that's moles. What do I want? Mass. I want grams. Periodic table. That's right. So multiply by 32 and bingo. You're going to end up with 1.32 grams of oxygen. Do the work. Make sure that's what you get. Thank you.